Good evening, millennials. Today we'll look at an interesting problem called validate binary search tree that is occasionally asked in FAANG interviews. So this is the 98th problem in the LeetCode website. So let's read the problem and discuss the shortest approach to it. So validate binary search tree. So you're given the root of a binary tree and we have to determine whether it's a valid binary search tree or not. So let's see what have we find a valid binary search tree as. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with the keys greater than the node's key. Both the left and right subtrees must also be binary search trees. Okay. So if you have no idea of binary search trees, please feel free to look at our other videos where we have explained what a binary search tree is. But let's just look at the example. Example 1, 2. So if you take 2, all the nodes to the left of it should be less than 2 and all the nodes to the right of it should be greater than 2. There's no equality here. So if you just look at 2, first one is less than 2 and 3 is greater than 2. So this is a valid binary tree. So we just return true. And in this case, if we see that 4 is less than 5, but it's to the right of 5. So this is not a valid binary search tree. So let's look at the constraints. The number of nodes in the tree is in the value 1 to 10 power 4. Okay, and each of the nodes value is between minus 2 power 31 and 2 power 31 minus 1. So let's remember these constraints. And we have given a structured tree node with val and left pointer and the right pointer and 3 constructors on how to construct the tree node. So let's try to write a basic recursion. When we reach a null node, it means that it's a valid binary search tree. So we return true in that case. Else, for each node, we need to check whether the left node and the right node are left node is lesser than the current root node and the right node is greater than the current root node. So we need to do this for everything. We can write a short way for this solution because we know that every node lies in the value between minus 2 power 31 and 2 power 31 minus 1, which fits in the long range. And so we can just check it in the recursion for each subtree, whether starting from the root, whether the left and right lies between this range. So the minimum one can get is minus 2 power 31 and maximum one can get is 2 power 31. So by using this, we can traverse the left and right subtree using a single function call and we can be able to check it. So let's try to write this in a single line. So as we have seen, if root is null, we just return true. So we just return root equal to null, or we need to check for the left and right subtrees, whether the left subtree's value is lesser than the node or the right subtree's value is greater than the node. But here our function definition is tree node star root. They have given only one value, but we need to have a lower limit and an upper limit to write it in a single function call. So let me just define another variable long low, and here we have to give it a default value because the function call is not visible in LeetCode, and hence you have to have a default value if nothing is passed. So I just give a long minimum and I declare another variable long high and I declare it as long underscore max because the value of the nodes lie between minus 2 power 31 and 2 power 31 minus 1. For each node I check whether the current value lies between the range for that given node. So it should be greater than low and its current value should be lesser than the high, because we are given the constraints it's between minus 2 power 31 and 2 power 31 minus 1. This is for every node, and for every node, from every node we need to traverse the left and right subtrees. So here I would just call the same function is valid BST with the left and right subtrees. Let me just resize my screen. So here instead of the root, it'll be root arrow left because we are traversing the left subtree, and the lower limit for this one would still remain low because the nodes on the left can still be lesser, should still be less than low, should be greater than low, but we can restrict our searching space to node arrow, to root arrow val, because the left subtree's value can never be greater than the parent node's value. So the maximum it can be is root arrow val, which is the higher value, and is valid binary search tree of, now I'm traversing the right subtree, root arrow val, comma, now the lower limit would be the it should be root arrow right, comma, now the lower limit would be root arrow val, because all the nodes on the right are greater than the root's value, and high, since the maximum possible is 2 power 31 minus 1. So this is the neatest and single line of code. This will traverse every node and then return values based on whether it's a binary search tree or not. So when it's true for everything, it'll return true, and in the recursive calls we get an and finally we get whether it's a valid binary search tree or not, and it'll return true. So let's just try to run this code. So it passes. I just ran it a few times. So as you can see, it beats 93% of C++ solutions, and it's the fastest and the most simplest and one-line code you can ever find. This is possible because we are given the constraint that the root node's value is between minus 2 power 31 and 2 power 31 minus 1. If it was not given, you need to write it greater than a single line. If you have any comments, please leave it down in the comments below, or if you can think of a better approach, please leave it down in the comments below, and we'll try to update our solution. Thank you.